right. So now that we have a quick overview of what cylindrical is and how it relates to polar, now it makes a little bit more sense to talk about this theorem 1. Triple integrals and cylindrical coordinates. Really, the first bit of this, saying what theta is between theta 1 and theta 2, r is between some r1 and r2 of theta. This is just what we did with double integrals in polar. So that's the same. Except for now, for the z, we have to worry about which surface is above the other. And then you set up your triple integral much like we did in polar. You convert your x's to what x is equal to in polar, r cosine theta, what y is equal to in polar, r sine theta, and since we're in cylindrical, z stays z. And then we even have the same differential area for polar, r dz dr d theta. All right, so let's get started on example 1. So example 1, we are to integrate z times the square root of x squared plus y squared over the cylinder x squared plus y squared less than or equal to 4 for z between 1 and 5. So first thing to keep in mind here is that we're not actually going to be sketching the function at all. The function that we're integrating, we never have to sketch it, ever. It's the boundary, it's the domain of integration that we need to sketch to figure out how to decompose it in a right way to write down the integral. So we're going to put a hold on the f of x, y, and z and just talk about the cylinder and the range for z. So x squared plus y squared, when it equals 4, this produces an actual cylindrical shell, let's say. It's only the cylinder itself. It's not actually filled in. So we can think of this as a hollow cylinder. So a cylindrical shell. If, however, we go ahead and introduce an inequality, then this is actually a solid cylinder. It's the same shell that we had, but then everything within. So if I draw my axes now, here's our cylindrical, our solid cylinder. So it's solid. Now we want z to be between 1 and 5. Well, z equals 1 is a plane parallel to the xy plane. Same thing for z equals 5. We have two different planes that chop this off. So really, this cylinder normally extends forever, right? Because if we look at these two equations here, there's no z in them, so z is free to move on forever. As soon as we take a look at z values between this plane and this plane, we're basically chopping the cylinder into these two bits, and we're getting this little sub-cylinder. So I'm going to go ahead and outline that. And really this is what we have. So all that stuff we don't actually have. So x-axis, y-axis, z-axis. This starts at a z value of 1 all the way up to a z value of 5. And that solid region there, that is going to constitute our domain of integration. Let's just call it W. So what we need to do is find the triple integral over the solid region. So our goal here is to find the triple integral over the solid region W of our function That is what we have to compute. Well, let's go ahead and describe W in terms of cylindrical coordinates. So for cylindrical coordinates, we start off by saying, what's the top and bottom surface? Well, the top surface is definitely z equals 5, and the bottom surface is z equals 1. All right? Now, if we can think about taking this entire cylinder here and then projecting it down into the xy plane, we would end up getting is a circle of radius 2. We get a shadow that looks like that. So if we then think of this in the xy plane, well, clearly the radius must range from 0 to 2, and theta must range from 0 to 2 pi, since we go all the way around, so theta equals 0 all the way around to theta equals 2 pi. And then we think about filling this in by starting with a small circle of radius 0, and then the circle bleeds outward, and it fills in sort of like a oil slick in water or something like that. It fills out until we get to radius, radius 2. So these right here are in fact the bounds. So when it comes time to set up this integral, what we're going to have here, start on the new page here. So the triple integral over W, z square root x squared plus y squared dv. Well, we just said that theta goes from 0 to 2 pi, r goes from 0 to 2, and z goes from 1 to 5. We have to now convert this, our function, into cylindrical coordinates. Well, in cylindrical, z stays z, so we keep that. And then this right here, the square root of x squared plus y squared, that's just r. Or if you want to think about it, the inside turns into r squared, and then the square root of it, it's plus or minus, but because r is represented as a distance, we take the positive root. So this whole thing turns into z times r. And as a reminder here, that dv for cylindrical is it's r dz dr d theta. So this becomes another r, so we get an r squared dz dr d theta. And now this integral right here is no different than, sure, we have different symbols here. We have z's, r's, and thetas, but we have a triple integral over a rectangle now. I know that this is not a rectangle, In Cartesian coordinates, this is a solid cylindrical, a solid cylinder. But in cylindrical coordinates, it's actually a rectangle, because this is a box. In the ZR theta plane, in three-dimensional space, ZR theta space, we actually have a rectangular prism. So this is a box. So this is just like a 15.3 day one triple integral problem. So that one's not bad at all. And for that reason, I'll just write down what the answer is, and I'm not going to waste time for the video evaluating this, which I'm sure you can all evaluate perfectly fine. So this ends up becoming, as soon as I look it up, pardon me, this is 64 pi. Oh wait, how did I get a pi in there? Oh, there we go. Not paying attention. All right.